Alrighty, welcome back to operating systems. So, this lecture should be quick. The long version's like 30 minutes because, well, unfortunately your final's coming up sooner than you would like, so you should probably finish lab 6 before that. So, let's see if we can do this in record time. So, where we left off before, we were doing least recently used. We said we couldn't implement it. So we're going to approximate it, and one of the approximations we're going to do is something called the clock algorithm. So we are talking about clock page replacement today. So the data structures involved here, we're keeping a circular list of pages in memory. This will allow us to figure out what page we need to evict. So circular, it will be a certain size, all the pages in memory, and it will be circular, so it will loop back on itself. So how this is going to work, we're going to keep track for every page in memory. We're going to have a reference bit associated with it that will keep track whether or not it has been referenced, and in the slides it will be in that light gray color. And this bit, we want our references to be as quick as possible. The quickest thing we can do on a computer is update a single bit whenever we reference something, and in fact, this is what our MMU does for us. So we essentially get this for free, so we don't have to worry about performance. This whole algorithm will take place whenever we do replacement and only replacement. So we don't care if that's a bit slow. We want our references to be as quick as possible. So other than that, we have a hand. You think of it as a clock. It's basically an iterator or pointer to the last element examined. And how the algorithm works is if we need to insert a new page, if we need to find something to kick out, then we check the hand's reference bit, so whatever thing its page is pointing at, check its reference bit. If it's 0, then it's out of here. So that means it hasn't been used in a while, so we kick it out. And then we placed the new page there, set its reference bit to 1 since we just used it, and then advance the hand to the next one. We'll see why that's evident, why we have to do that, because essentially this is like a 2-strike system. We don't want a strike to count against it, and again, we'll see that in a little bit. The other option here is if the current page we're pointing at has a reference bit of 1, means we've used it somewhat recently, so we just set that bit from a 1 to a 0, and then we advance the hand and repeat this process until we actually find a place for this page to go. And then for page accesses, all we do is set the reference bit associated with that page to 1. We want it to be as quick as possible. So again, we'll assume that our memory can hold a certain number of pages, in this case 4, and then we have the following accesses like before. Only difference now is I'm drawing this little clock. So initially, if we have 4 pages, well, we have a circular buffer of pages. Initially, I'll just say they're all 0 to say they're invalid. So the first reference points to the second, points to the third, points to the fourth, and then that points back to the first reference. So it is a circular list of pages with a reference bit. And then this little thing is the hand. That is the current element we're pointing in. And if you use your imagination, it looks like a clock. That's why it's called the clock algorithm. So if we access page 1, we follow all the rules. So the hand is currently pointing at something with the reference bit is 0. Well, it's not even valid anyways, so we place our new page here, right? So we place our new page here, set its reference bit to 1, so its reference is in the bottom cell here, and then we advance the hand. So everyone okay with that? All right, 2, what happens? Yeah, same thing. So the hand's currently pointing here. The reference bit is 0. So I place it there. So page 2, reference bit is 1, advance the hand, and I'm done. All right, this is kind of boring like before, right? So first 4 accesses. I'm going to have to populate it. So I insert a 3, reference bit is 1, advance the hand. Insert a 4, reference bit is 1, advance the hand. All right, now the fun part. We reference page 5. What happens if we follow the algorithm to the letter? So we're currently pointing at page 1. Its reference bit is 1. Do we toss it out? No, right? We just set its reference bit from 1 to 0 and then advance the hand, trying to find another victim. Now in this case, you can kind of see where it's going. We're going all around the world. We're going to check everything once. So this reference bit is 1. I change it from a 1 to a 0, advance the hand. Same thing for page 3, 1 to a 0, advance the hand. Same thing for this. It's 1, change it to 0, advance the hand. The shortcut for it the first time, I could have skipped all those steps if I just set all the 1s to 0 because I know it's going to spin all the way around. So if you want to do it faster, that's your shortcut. All right, so now I'm pointing at this page. Do I kick page 1 out? Sure do. So I replace page 1 with page 5, set the reference bit for page 5 as a 1, and then advance the hand. So after page 5, my clock looks like this. Everyone still with me? Perfect. So now we access page 2. What happens? Yeah, so that's a hit. It's in memory. But I'm going to, since I just referenced it, I'm going to set its reference bit from a 0 to a 1 now. So I actually do something when it's in memory now. So I set that 2, or the reference bit for page 2 to a 1. And now, well, this looks more kind of like least recently used. I have now used it. If its reference bit is 1, it means it gets a second shot at life. It means I'm not going to immediately kick it out. All right, now I access page 3. What happens? Yeah, same thing. I set the reference bit for page 3 from a 0 to a 1. And again, for references, things that are in memory, don't try and play with the hand or anything like that. Don't move the iterator. Don't try and do page replacement. If it's in memory, all we're doing is flipping a single bit at most. So now we access page 1. What do we do?
Set
3 to 0. No, we have to go with what we're currently pointing at. Yeah, so currently we're pointing at page 2. Its reference bit is 1. Yeah.
Oh, so like the hand does not change to if we just access already existing page, right?
Yeah, if it's a page hit, you're not advancing the hand. That's slow. We're just updating references if it's a hit. That's it. Flip 1 bit. So now we follow the algorithm for the replacement. So we're accessing page 1. So do we kick out page 2? No, its reference bit is 1. So we just put a strike against it. So its reference bit goes from 1 to 0. And we advance the hand looking for our victim. Do we kick out page 3? Nope. So we just set its reference bit from 1 to 0, advance the hand. Now we're pointing at our victim. Page 4, its reference bit is 0, so it gets evicted. So we kick it out for page 1, set page 1's reference bit to 1, and then advance the hand. And you can see why we advance the hand. Otherwise, on our next miss, we're going to immediately set 1's reference bit from a 1 to a 0. Which doesn't make sense since we just put it in. So that's why we advance the hand after we put something in. All right, so now we access page 2. What do we do?
Set 2 as well.
Yeah, all we do, don't touch the hand, don't touch anything. Just set 2's reference bit from a 0 to a 1. If it's already a 1, you can, if it makes you feel better, you can change it from a 1 to a 1. All right, now we access page 3. Boom, its reference bit is 1. So now we are done. If we wrote this out, so typically that little diagram you just have as you're going through it to actually say what pages you're replacing. It would look like exactly like the diagram we have yesterday. So the first 4 accesses were all misses, and then going back to our diagram before, we replaced page 1 with page 5. Then on this diagram, it doesn't have to do with the hand. That's the actual algorithm. So 2 and 3 were a hit. And then when we access page 1 again, we threw out page 4, right? So we threw out page 4, and then the next 2 were hits. So in this case, our number of page faults is 6. Fun, huh? All right. So Do we want to do it for this example? Do we want to have fun, play with a clock? Sure. All right, let's do it. So this is the same sequence we had in the last lecture when we were going through it. So for questions like this, you probably want to use a corner of the paper or something like that. Draw the little clock. So here, I'll draw my clock. Wow, it's this cursed room. So I'll draw my clock. Initially, it's all empty, and my hand points here. So if I have 4 pages, well, I have a circular list of 4 pages as part of my clock algorithm. And then for all of the accesses, yeah, I'll just write it in blue. So first access, if I access page 1, what do I do? Just put 1 in, advance the hand, right? 1, reference bit is 1, advance the hand. If I wanted to do the first 4 very quickly, how could I just do the first 4 very, very quickly?
Just don't move just keep the hand at 1 and just...
Yes. Everyone okay to do the fast version? So fast version is just keep the hand at the first element and just populate the first 4, set all its reference bits to 1, and just populate them in order. So next thing we populated was 2, reference bit is 1, then 3, reference bit is 1, 4, reference bit is 1. Now we are at this reference, right? So if I was to draw all of our page faults, well, the first access we brought 1 into memory, second one we brought 2 into memory, third one we brought 3 into memory, fourth one we brought 4 into memory. So it would look something like this. All right, we're okay with that? All right, so now if we access element 1 or page 1, what happens? Yeah?
It's already 1. The bit is already 1.
Yeah, the bit's already 1, so I don't have to do anything. If it makes you feel good, then you can erase this 1 here and then write down a 1. So, or you could just not do it, but if that makes you feel good, who am I to stop you? So next one we access, nothing happens. Page 1 and page 2 are in memory. The reference bits are already 1. So I'll just take the shortcut and say that nothing happens. All right, now we access page 5. Do we want to take the shortcut or do the slow version? So shortcut is, this is something new. I'm going to have to run the algorithm. If all of the pages are currently have their reference bit as 1, I could go around the entire clock, or I could just do the fast version and set all the 1s to 0. Okay, setting all the 1s to 0? All right, so let's set all the 1s to 0, do the fast version. Zero, 0, 0. So now it looks like this. We're accessing page 5, so what are we kicking out? Page 1, right? So we are kicking out page 1 with page 5. So in our diagram, it will look like this. Now we actually have to place it. So I put in page 5, reference bit is 1. Am I done? Yeah, advance the hand when after I put it in. So now it looks like this. So everyone okay with that? All right, now, whoopsies, now I access element 1. What happens? Yeah, so current hand is at 2, reference bit is 0. So that is donezo. It is out of here. So I'm replacing 2 with a 1, which seems like a bad idea, but we just follow the algorithm. So 2 gets replaced by 1. Its reference bit is 1, and we advance the hand. Now we still have 5. We replace 2 with 1, and we look like that. So everyone good again? All right, so now we access page 2. What happens? Should be kind of boring at this point, right? So we're accessing page 2. Hand is currently pointing at 3. Its reference bit is 0, so it is donezo. So see you later. I'll replace it with 2. Advance the hand. So I would just place 3 with 2. Well, turns out that was a fairly poor idea. Now I access page 3 again. So I kick out page 4 for page 3. Are we bored yet? All right, we're all bored. So this is just going to keep on page faulting till the end because, well, at this point, I'm just replacing things in essentially FIFO order. It's not really helping me at this point. So if I put a clock algorithm on the final, you'll do well on it, right? Perfect, deal. All right, so let's see if we can wrap up real quick. So like I said before in the previous lecture, for performance, you might choose to disable swapping altogether. Memory is cheap, has quite high capacity. If you can throw money at the problem, like if you're Google, you would rather spend more money to increase your performance. So you'd rather just let programs using too much memory die. What Linux will do is if your one process is using, or if you run out of memory on your system, it will run something called the OOM, or out of memory killer, where it essentially just picks a random process and kills it to free memory. So basically, just pick something to kill, send sig kill to it, kill -9, boom, it's done, boom, you have free memory, we have fixed the problem. There's also some different things we can do with virtual memory. So we can have larger page sizes. So essentially, we can skip out on the lowest level of page tables and use those bits all for a larger page. So on some systems or on Linux, you can use something called a huge page, which makes the pages 2 megabytes. Or if you go up to the next biggest size, so the next 2 to the 9 bigger, you can have pages of size 1 gigabyte, and they are creatively called gigapages. So the whole trade-off here is you trade off more fragmentation for more TLB coverage. So the TLB can only store a certain number of entries. By default, each entry covers 4 kilobytes, the size of a page. So you can't really cover that much with the same number of entries. Say your TLB holds 10 entries, then it can essentially cover 40 kilobytes of memory translations. If you use huge pages, then, well, now if I have the same 10 entries, I can cover 20 megabytes, which is a lot bigger. So there's some trade-off here. If your program uses only like 4 kilobytes or 8 kilobytes or something like that, that would be exactly 2 pages. Well, if you're using a huge page, a lot of that space, a lot of that 2 megabytes is wasted. So wasted memory we call fragmentation. That's basically a trade-off we have now. There's a move right now to have more support for huge pages. All right, so that was the little aside. We can wrap up now because we just went over the clock algorithm. So it's an approximation of LRU that we can actually implement. The key data structures are a circular list of pages in memory. Each page has a reference bit. Yeah?
Sorry, what did you mean by TLB? Like when you said how much TLB?
TLB, translation look aside buffer from virtual memory. Basically a cache for doing all the translations. So there's only a certain number of entries it can cache, like page table entries. Basically a cache for page table entries. Yeah?
Can you just re-explain how using a larger page size would allow you to have more TLB entries?
No, not more TLB entries, a bigger reach. So if each entry covers a page, right? Which is 4 kilobytes. But yeah, if we used a huge page, each entry covers way more space. Yeah. Yeah.
So like that would just reduce the number of need to switch pages, I guess. That's why we need a bigger page. Like the bigger page reduce the need to swap pages, I guess.
No, the bigger page, just one entry, one page table entry covers way more memory. That's it. Might be good for performance. It's less translations you have to do, right? If I use 2 pages, it's the same translation. I don't have to retranslate it or do anything. Yeah. All right, so yeah, with the clock algorithm, a circular list of pages in memory. Each page has a reference bit associated with it. It was light gray in the slides. Then it has a hand, which is an iterator pointing to the last element examined. The algorithm that only runs when you're doing page replacement, where this page you are trying to access is not in memory. Check the hand's reference bit. If it's 0, place the page there, set its reference bit to 1, advance the hand. If what it's currently pointing at has a reference bit of 1, we set it to 0. It just gets a strike against it, and then we advance the hand and repeat until we actually find our victim. And then for accesses, we do the fastest thing we can, which is just set a bit. If the bit of that page is a 0, we set it to a 1. If it's already a 1, we leave it alone. So with that, I will stick around. If you haven't looked at Lab 6 yet, you should. I will stick around to help you if you have